You are in a submarine. It is night on the surface. Far above you, a warship is sweeping the sea with active sonar, a bright pulse. A second later, a distant metallic echo. They have your approximate bearing. They know you exist. The captain gives a simple order. Take us deeper, under the layer. The boat tilts down. The water outside grows colder and darker. But something else changes too, something you cannot see. The next sonar ping arrives. This time the echo is weaker. Then, for several pulses in a row, nothing. On the surface, the ship's sonar screen goes quiet. The contact has not magically vanished. It has simply crossed an invisible border. Not a border on the map, a border in physics. In this episode of Silent Oceans, we explore that invisible border, the thermocline, one of the most important and least visible layers in the ocean. 1. The ocean is not just deep. If you look at a satellite map of the sea, it feels simple. Blue areas that are shallow and blue areas that are deep. But for sound, the ocean is never just deep. It is layered. The top is usually warmer, mixed by wind and waves. Below that, the water quickly becomes colder. And far down, it is dark, dense, and almost uniformly cold. This middle transition, the zone where temperature drops rapidly with depth, is called the thermocline. In physical terms, temperature changes quickly with depth. This changes density, and density changes the speed of sound in water. Sound does not move at the same speed everywhere in the ocean. It is faster in warmer water, and also changes with pressure and salinity, that is, with depth and salt content. Overlay. Sound speed depends on temp, pressure, salinity. So if you drew a graph of sound speed versus depth, you would not see a flat line, you would see a curve. And curves bend things. 2. Refraction. Why sound rays curve in the sea. On land, we are used to sound traveling in almost straight lines, at least over short distances. In the ocean, that picture is incomplete. Here, sound behaves a bit like light passing through glass. When it moves from one medium to another, from warm water to cold water, or from low pressure to high pressure, its speed changes. And when speed changes gradually, sound waves bend. This bending is called refraction. Imagine a series of sonar pulses traveling down into the water. Each pulse is a bundle of sound waves. As the waves enter the thermocline, they pass through layers where sound speed is different. Some parts of the wavefront move slightly faster, some slightly slower. Over many meters, this tiny difference adds up, and the sound path curves. In a simple rule of thumb, sound bends toward regions where it travels slower. If the upper layer is warm and fast, and the layer below is colder and slower, many sound rays curve downward into the slower region, then later curve back up again. The result is an acoustic lens. Some depths receive a lot of sonar energy, other depths receive almost none. These almost none regions are called shadow zones. From above, it looks like this. A ship sends out a fan of sound. Some rays hit the submarine directly, others are bent away and never reach its depth. The geometry of the layers decides which case you are in. That invisible geometry is the true battlefield of submarine warfare. 3. Shadow zones, where sonar sees nothing. Let's go back to our submarine hiding under the layer. The layer here is the seasonal thermocline, a temperature gradient that appears in many oceans during warmer months. On a cross-section you would see a warm, mixed surface layer, maybe 50 to 100 meters thick. A thermocline where temperature drops quickly. A colder, more stable, deep layer below. The ship's sonar sits in the warm surface layer. Its pings travel outward and downward. Some energy reflects off the rough sea surface. Some is scattered by plankton, bubbles, and tiny suspended particles. And some is bent downward at the thermocline, then bent again and lost into deeper water. If the submarine sits at just the right depth below the thermocline, the sound that would hit it gets deflected away. From the ship's perspective, the sonar screen grows quiet in that direction. The operators can still see background clutter, but the clear, bright contact is gone. This is a shadow zone in action. But it is crucial to understand something. Shadow zones are not empty. They are simply less illuminated by sound. If you increase power, change the angle, or use a different frequency, some energy may still get in. And the ocean is not a perfect lens. It is a messy, moving, noisy system. Shadow zones are places where probability changes, not where physics stops. 4. Deep ocean versus shallow seas. So far, we have implicitly been in the deep ocean, hundreds or thousands of meters of water with room for large, smooth temperature gradients. Deep water is paradoxical. It is dangerous for submarines because sound can travel incredibly far, but it also allows stable acoustic channels and predictable layers. In some regions, a combination of temperature and pressure creates a sound channel where sound rays are trapped and can travel thousands of kilometers with relatively little loss. From a detection perspective, this can be good or bad. Good if you are listening, you can hear faraway events. Bad if you are noisy, someone else can hear you. Now contrast this with shallow coastal waters, the so-called littoral zones. Here, the depth might be only 50 or 100 meters. The bottom is close. Waves mix the surface. Rivers bring in fresh water. The temperature profile is jagged and unstable. Sound in shallow water bounces between the surface and the sea floor, interacts with sand, mud, rocks, and man-made structures, picks up noise from ships, fishing, and coastal life. For sonar, this is a nightmare. Reflections create a forest of false echoes. Small changes in tide or temperature can completely alter performance. For submarines, it is complicated. Shallow water can mask you because everything is loud and messy, but it can also expose you because there are fewer places to hide vertically, and the bottom itself can reflect your noise. In deep water, layers are your allies or enemies. In shallow water, the boundaries, surface and seafloor, join the game. Either way, the key insight is the same. Sonar range is not a fixed number. It is a moving target, set by the state of the ocean itself. 5. The limits of the layer. How navies fight back. It is tempting to think of the thermocline as a kind of stealth switch. Just dive under the layer and you are safe. Reality is less comforting. Modern navies know about thermoclines. They measure them, model them, and exploit them. A surface ship can lower a variable depth sonar, a towed body that can be placed at different depths. Helicopters can deploy dipping sonar, lowering a small sonar head into the water to look under the surface layer. Aircraft can drop sonobuoys, floating sensors that listen at multiple depths, then send data back by radio. Submarines themselves carry environmental sensors. They can measure local temperature profiles and estimate where the sound will bend. But there are always uncertainties. The ocean changes with time of day, weather fronts, seasons, currents and eddies. A layer that looked strong in the model might be weaker in reality. A shadow zone might have holes. An assumed safe depth might suddenly become loud. This is where we meet an important theme of Aeon Scientia. Models are not truth. They are maps of probability. And in submarine warfare, probability is often the difference between detection and escape. 6. 3 heuristics for thinking in layers. We are not all sonar officers. Most of us will never sit in front of a sonar screen. But the way we think about sonar and about the thermocline can teach us something general about complex systems. Here are 3 simple heuristics. Heuristic 1. When you see a single performance number, ask about the hidden layers behind it. If someone says, "This sonar has a range of 20 kilometers," that is like saying, "This city is 20 minutes away." 20 minutes. In which direction? At what speed? At rush hour or at night? In the same way, a sonar range without context ignores thermoclines, depth and noise. The real question is, Under which conditions? And what is the structure of the ocean in this scenario? Heuristic 2. When you hear stealth, translate it to shifted probability, not zero risk. Diving under a thermocline does not make a submarine invisible. It reduces the chance that certain sensors will see it from certain angles. It increases the chance of survival, but it never guarantees it. The same is true for many technologies: encryption, firewalls, stealth aircraft. They bend probabilities in your favor. They do not cancel out the game. Heuristic 3. Replace on-off thinking with maps of risk and opportunity. The ocean is not simply safe or unsafe. It is a landscape of better and worse depths, of louder and quieter layers, of more and less likely detection. When you imagine a complex system, a network, an economy, even your own habits, try to picture it like the layered ocean, not as a switch, but as a shifting field of higher and lower risk. 7. Circular close, back to the invisible border. Let's return to our opening scene. The submarine dives. It passes through the warm surface layer, through the rapid change of the thermocline, into the colder, more stable, deep water. On the surface, the sonar screen loses the clear echo. Nothing supernatural has happened. No Hollywood stealth mode was activated. A model changed. The sound rays now bend differently. Some are trapped above the layer. Some dive too steeply and miss the submarine. The ship's sensor, which once had a clear line of sound, now peers into a shadow zone. For the crew underwater, this is not just luck. It is design. They are navigating not just in space, but in structure, using the hidden architecture of the sea itself. In the next episodes of Silent Oceans, we will keep following that architecture. Because the ocean is not only a place where submarines hide, it is a layered machine, and understanding those layers is the first step to seeing through the silence.